Hello, community. We always try to improve our large language model. And a year ago, Stanford University gave us here DSPy, a self-improving machine learning system. But now, some days ago, Stanford published their latest research, and it is called TextGrad. And it is able to do an automatic differentiation via text. Now, TextGrad, and you get it, is of course a reference to AutoGrad. In AutoGrad, we have access to the tensors within the layers of our large language model. Now, with TextGrad, we do not have access. Think about GPT-4 Omni, where we cannot dive here into the specific layer structure, in the specific tensors. So therefore, what we do, or what Stanford did, is invent a code extension to PyTorch, and all is now open source and you can use it. And to give you here the overview, what we have, more or less we have two AI systems. Let's say on the one hand side we have GPT-4 Omni, and the other one we have the GPT system or any other open source LLM that you like that we want to optimize. So how does it work? Easy. We have API calls between those LLM systems, and the task is simple: to find the best prompt. So we are at programming here, prompt engineering for a very specific task on exactly this LLM. Now you know that this is now a very sensitive topic, given that this, let's say it's GPT 3.5, has a given pre-training. It has a given fine-tuning. It was given instruction how to behave. It was given an alignment like DPO, how to behave as a system in the responses. It was trained on an instruction set with a given complexity, and it is only to solve up to a certain level of reasoning task, given all the pre-training that's happened. But immediately you understand that this also is valid here for our more intelligent LLM, our evaluator, our teacher LLM. So this is now an interesting play where we have now very code simple in a PyTorch extension to do this automatically. Now, to give you the final result, I code this now for a week, and I have to say, in my domain, science, for my task, very much logical reasoning, TextGrad is significant better performant than DSPy. So let's have a closer look at this. We will start with AutoGrad, just for my green grasshoppers to remember this, then DSPy, and then we focus on natural language gradients, which is here something beautiful in TextGrad, and then I show you the new code extension and I give you 4 notebooks that you can try it out yourself immediately, and it is open source. So for my green grasshoppers, hello, great that you are back. Now, I know that you know how AutoGrad works, but just to have here the certain level that we all know, we have a forward pass. The neural network makes prediction by processing the input data to its layers, and this pass computes the loss function, which measures the difference between the network's prediction and the actual target values. Now, during the forward pass, the AutoGrad system records all the operation performed on the tensors in a direct acyclic graph, and you know it. Now, in the backward pass, once the forward pass is completed, the loss is calculated, the backward pass begins, and AutoGrad computes the gradients of the loss function with respect to each tensor, each parameter that contributes to the loss. This is done by traversing the DAG from the loss tensor back to the input tensor, and using here a simple chain rule of calculus, the AutoGrad accumulates here the partial derivatives of the loss function with respect to each tensor. And then we do simply a gradient update. Now, you know that this is, if you want, the computational mathematical view of this. And now we take exactly this logic, this pseudocode, if you want, and we build on this. The core feature of AutoGrad, if you remember, is its ability to perform automatic differentiation. This means it can automatically compute derivatives of complex function, and this is of course essential for our deep neural network operation. Plus, remember in PyTorch, those AutoGrad systems use a dynamic computation graph, which are built on the fly during the forward pass. And this is exactly what we will need and what Stanford implemented now in its new methodology. So 2 points to remember: automatic differentiation by the system and a dynamic computation graph structure. Now, if you go to GitHub, here you are, TextGrad. It is beautiful because, as I told you, it is open source. It is an AutoGrad engine, but now, since we do not have access to the tensors itself, for textual gradients. More or less, that's all there is to it. However, the implementation is really beautiful. So let's have a look at this. Those are the 2 contributors. Thank you for publishing this and making it open source for the community. It is done in Python, as you can see. And here you have the GitHub link for you to discover this yourself. Just to show you, they operate here with an analogy. And it's a very abstract form, but it's very helpful. Because they say what we have. Normally we have an input, we have a model, our LLM, then we calculate the loss function, and we have an optimizer, Adam for example. So in mathematical terms, this is easy. Those are those 4 elements. Now in PyTorch, remember, cross-entropy loss and gradient descent? You know this from PyTorch. And now in TextGrad, they follow this idea here in PyTorch implementation really close by. So what we have here now, the input is now a variable. The model is a black box LLM. The loss is now a text loss, since we can only operate with the input and output of proprietary LLMs. And our optimizer is now something beautiful. It's a text gradient descent module. And more about this in a minute. Now Stanford tells us, hey, if you know PyTorch, you know 80% of TextGrad. You know, I'm coding this now for more a week. I have to tell you, no, this is not correct. You know 20% of TextGrad, but more about this later. So what is nice, Stanford gives us here 4 Colab notebooks that you can jump in. And I would recommend you start immediately with a number 1, and then you move here to prompt optimization. Try it out yourself, get your hands here deep into the code, but it is a beautiful implementation and it is very powerful. And if you missed out on DSPy, the good thing is it is built on DSPy, and now it's a year later, and now you have all those optimization and maybe even clearer implementation now in this particular code. So here you see a very short Python program. This is all. This is number 3. Here is the prompt optimization. You install here pip install TextGrad. Then you have your all. Yeah, you need an open API key, of course, where you have to pay OpenAI that you can use here. The GPT-0 system, the Omni system, and what we want to optimize the prompts are for a system that's not so intelligent. So GPT 3.5 Turbo 0125. Great. So you see, you run here to this, you define here the different function, the evaluation set, the validation. Yes, and then you have everything from the train, validation, and test data set. And then you start here with example here, the data loader, and you know all of this. And then you just let the system run and optimize itself. So the code is rather easy, but we have to understand what is happening here behind the code. How is this possible that TextGrad is working so beautifully? Now, what they tell us, they had 2 main inputs to design, to create the new model. And the first input was, of course, DSPy. So the idea of viewing here a complex LLM-based system as programs with many layers, and this proposes way to build and optimize them in a programmatic fashion. And after a year, yes, this is DSPy here, you have the GitHub, you have here a Colab notebook to get started, or you have a look here at my playlist. I have a playlist with 8 videos. I explain DSPy, I show you the program, the AI pipelines. I show you here if you use ICL RAG classification, I explain the code to you, and I give you even a little bit outlook how to improve the system. But the second part is now a part I have never shown you on this channel. And this is also new to me. And this is prompt optimization with textual gradients. Prodigy. Now, Prodigy, you have to be careful because this is the key to understand here this new methodology. And I tried to read it without understanding what Prodigy is, and I failed. So, Prodigy is built on the textual gradient analogy. And I tried to implement it, but no, they just use here the analogy of it, and they implement it in a much simpler way than you would imagine. But of course, this analogy is here what we call now automatic differentiation on text. So let's have a look at this maybe. This is the original study, Microsoft Azure AI, a very nice study. I would recommend you read it, although it's from October 2023. And they explain here in detail the automatic prompt optimization with gradient descent and beam search. Now, let me give you three main facts you have to know about it. It acts here like a numerical gradient calculation, but now we are not in the numerical space, but now we are operating in the semantic space. But since we do not have access to the vector representation of the semantic space, we have to use here simply the sentences. So we are now operating here on a semantic level, but what they do, they generate here through a feedback loop where the LLM critiques the current prompt, either from itself, but better is you have two LLMs, by identifying and describing its shortcoming. So you have one teacher LLM like GPT-4, and the other one is GPT 3.5, whatever you have on an open source LLM. And this more intelligent LLM identifies and describes the shortcoming given a specific task to GPT 3.5 and how GPT 3.5 responds. And then we run to a cycle of self-improvement. So prompt editing, so adjusting now the next iteration of a maybe better prompt by addressing the issues highlighted by the natural language gradients. Uses another set of LLM instructions to modify the prompt in a way that it moves, careful, semantically opposite to the problem described by the gradients. So if, let's say, GPT-4 says, hey, GPT 3.5, in your answer you forgot a fact, yeah? So now the instruction from GPT-4 to GPT-3 is, hey, semantically opposite to the problem, include now new facts, maybe include this specific fact, analyze this specific sector that you forgot to analyze, and of course, described here by textual gradients. And this is exactly what this is all about in this topic. Yeah, then you have beam search and bandit selection, which is not so important, but what it does now in a summary, this now Prodigy integrates learning from mistake through feedback on existing prompts with a strategic exploration of new prompt configuration. Imagine beam search, aiming to find here the optimal configuration or the optimal prompt structure in fewer steps. And it does this in a more intelligent way than in DSPy and in a different methodology. However, honestly, this requires quite some API calls happening between those systems, which can be computational expensive. So I would recommend you do it once here to find an optimal prompt structure for one particular problem, and then you can reuse this particular prompt. And I will show you an example in a second. Okay, for migraine grasshoppers, so what we have a LLM that generates something. This giant model, like say GPT 3.5, generates an initial response based on the current prompt. And you might consider this the primary LLM prompt that you are trying to optimize, but not you handcrafted as a human, but you ask the help of another LLM, let's say GPT-4. And it operates by processing input data according to the existing prompt and generate output that are then assessed for their quality and accuracy, assessed by the critique LLM or GPT-4 or whatever you like. So this new model critiques the output from the generation LLM. It analyzes how well the prompt guided here the generation of response and identifies the specific weaknesses in the prompt. And then the critique LLM generates what the method refers to as natural language gradients. This is important. Natural language gradients, which are essentially detailed feedback on how the prompt could be altered to yield a better response. And you see, this is exactly here when we have a gradient descent. Now we go exactly in the semantic space in a different direction. So this feedback mimics here the function of the gradients into traditional AutoGrad numerical optimization by pointing out the direction which the prompt should be modified in order to improve its performance. But you immediately understand what is here the limitation. GPT-4 thinks it is in its own way, but GPT 3.5 is only able to handle a certain complexity level of tasks. Now, if you prefer to see this, what I just explained to you verbally in a pseudocode, from the publication here you have the complete pseudocode of Prodigy. Now, for example, line 5 here is explained here a little bit more in detail, and then you have line 7 explained, and then another line 7 here in the algorithms explained even further. So if you like the visualization of a pseudocode to help you thinking through this, this is the way to do it. Now, let me come back here to this concept of modifying a prompt to move semantically opposite. Because this is not where you say, hey, this is a mathematical clear definition. So what we want to do, we want to improve here the performance of the model, the output that is generated, but not by learning new facts or learning new knowledge or having a new pre-training, but through prompt optimization, prompt engineering. But now we want to do this here in an automatic way with the natural language gradient optimization. And this process here mimics, this is the analogy, the numerical gradient descent, but is here applied in the semantic or language-based context. Beautiful. As I told you, it all depends on the cleverness of the LLMs, or to be more specific, on the pre-trained complexity level that this LLM is able to handle and analyze. And if a gradient descent that a prompt is too weak, make it more specific would be a move in the opposite direction. So whatever GPT-4 notices here in the output of GPT 3.5, it tries to move in the opposite direction, whatever this is. And since we are here in the semantic space, it all depends here now, let me put it in a more mathematical way, in the vector embeddings of the semantic space that GPT-4 learned during its pre-training phase. Nice. Okay, beautiful. So here we are. Nothing new that we learned now. There's no additional training to GPT 3.5. We just optimize here the prompt to probe GPT 3.5 that we can get the best out of GPT 3.5 without learning GPT 3.5 anything new. We are just trying to squeeze out the best performance of GPT 3.5 or your open source LLM. If you have a 7 billion or 3 billion LLM, this is interesting. Okay, but now let's come to the main study. You see, June 11, 2024, Stanford University, TextGrad, the automatic differentiation via text. And now we need everything that we just learned today, and we build on it and we will develop a new methodology. So again, let's come back here to AutoGrad, the numerical calculation of backpropagation here using numerical gradients in our network. And then they say we use now this analogon, the same idea on different complexity levels on different objects. And as you can see here in this visualization, you can use it here, prompt for an LLM, a query for a search engine, or a tool prompt if you call specific tools. And yes, we are talking here about multi-AI agent system. A little bit later, I will give you even more complex definition. And we have here an optimization circle that is happening. Beautiful. Again, I already showed you here this kind of analogy in the abstraction space, either mathematically or in the PyTorch notation, or now in the complete new TextGrad code extension that you have to get familiar yourself with the 4 officially Jupyter notebooks published by Stanford University, which I highly recommend you have a look at. Now the nice thing, since this is now, if you abstract it away from a pure prompt structure, you can use this also for a molecule optimization if you do here an optimization by LLMs or vision language models. And of course, you can use the same methodology for a better interaction of the LLM now with a code LLM. And you have here coded at the iteration t, and then here you have exactly here these gradients that come back, that analyze it, that tries to improve the code here, and then you have here the better code at iteration t plus 1. So you see, you are depending now here on the intelligence, let's say, of two LLM systems or multi-LLM systems. If you think about, you can make this in a network of LLMs. Great. But I would like to give you here an official example here for prompt optimization, that you get a feeling. How good is it? What is it? What's happening? So we start with a prompt. Let's say you write this prompt and it says, hey, LLM, you will answer a reasoning question. Think step by step. The last line of your response should be the following format. Answer where value is a numerical value. And then you try this on, let's say, GPT 3.5 or Mistral 7b or whatever open source you like, and you get an accuracy of 77%. Great. Now, if you run through TextGrad, if you do this coding that I showed you, the 4 notebooks, the third notebook is exactly for this example, how to optimize this. And after it run, you will get now a better prompt, an automated programming prompt engineering. And now the new prompt is as follows. You will answer a reasoning question, the same. But now, list each item and its quantity in a clear and consistent format, such as item, quantity, sum the values directly from the list, and provide a concise summation. Ensure the final answer is clearly indicated in this format. You give it a format where the value is a numerical value. Then you go on, verify the relevance of each item to the context of the query, and handle potential errors or ambiguities in the input. Finally, double check the final count to ensure accuracy. And with this particular prompt on the same GPT 3.5, you get now an accuracy of 92%. Isn't that beautiful? So you see, the main task is not to learn something new to GPT 3.5, to fine-tune or to align it or to whatever extend its domain knowledge. No, it is here configuration of 2 or more LLMs to optimize the prompt structure for a given LLM, and we call it, if you want, a programming prompt engineering. So no hand optimization of your prompt, because you can run this, 100 times, 500 times, 1,000 times, and you get here for a specific model the best way to do it. Now, as I showed you with the pseudocode, you might like to have here, on the left side here, the mathematical notation from the numerical AutoGrad operation. This is this one here. And on the right side, you have now the verbal, how we do this now here, the implementation for the gradient operator. So you're familiar with AutoGrad, and now what we say now in this new methodology here is, hey, here's a conversation with an LLM, some sentences, some dialogues, plus you say, here's the conversation. Below is now the criticism of GPT-4 on particular parts in this conversation. And now explain how to improve here that we get a better result, how to improve here the prompt structure, the prompt sequence, or the prompt complexity itself. Maybe include causal reasoning. So you see, however you like to see it, this is the analogon that they stress here in their publication. Of course, it can be a little bit more challenging because you remember in DSPy we had those optimizers. And here too we have optimizers, and in the standard gradient descent, the AutoGrad for example, the current value of the variable is combined here with the gradient through subtraction. So you have this simple mathematical operation. And now updating this now but not in the numerical gradient descent, but now in the textual gradient descent. In our new library, we have now the command textual gradient descent, TGD step, and you can do this in a prompt. So if you want to see this pseudocode implementation, you say LLM, below are the criticism of X, incorporate the criticism and produce a new variable. And this variable might be a subset for a better prompt optimization, or if you go to more complex systems, I will show you in a minute. But please note, my green grasshoppers, depending on the complexity level of this LLM that it has been pre-trained on, and maybe you eliminate here the alignment of the LLM because you don't want here standardized predefined answers, but you need an LLM that is really free, quotation mark, to give you here also a harsh criticism. And given the causal reasoning capability of this particular LLM, in our case a GPT-4 and a GPT-3.5, or maybe easier, you have a Mistral 7B and a Phi 3 Mini, you have to be really careful that you do not cross the threshold of complexity level or causal reasoning threshold that one of the systems is simply not able to perform. And the one system, GPT 3.5, must still be able to understand the complex answer of GPT-4. Otherwise, GPT 3.5 is lost. So after a week of experimenting with this is a real sensitive equilibrium that you have to be careful if you go to more complex causal reasoning tasks. Now, I know that you want to see the performance benchmark between DSPy and TextGrad. Okay, let's have a look at this. So now we optimize a system prompt for GPT 3.5 Turbo using GPT-4 Omni as the gradient engine here that provides here the analytic feedback during this textual backpropagation. Beautiful. Let's start here with object counting. So if we have here a chain of thought, 0 shot, we get an accuracy of 77.8. With DSPy, please notice, we have 8 demonstration, we get 84. And with TextGrad, with 0 demonstration, we get close to 92%. Now, word sorting, we do the same, chain of thought, 0 shot, 76. DSPy with 8 demonstration, 79.8. And TextGrad with 0 demonstration, identical to DSPy with 8 demonstration. And the same is true for different dataset. So you see, even without any demonstration, TextGrad at least achieves the same performance like DSPy, but with 0 demonstration, which is really nice. From the original literature, let me show you this. And again, they have here this analogon of the numerical optimization and of the automatic differentiation, and with this beautiful TextGrad, can be complex and potentially non-differentiable function where the domain and the codomain of the function can be unstructured data. Yes. And they show us here a simple loss function for a code snippet. So if a code LLM can be the following. So you have, if you want here, the loss function depending on the code and your target goal that you want to achieve and the code optimization task. So for the LLM, this means, hey, here's your code snippet. This is the code. And here's the goal for this snippet. Whatever you want to achieve, faster, shorter, use another library, whatever. And then you evaluate the snippet for the correctness and the runtime complexity, for example. And then the author Stanford specifies here where we can use this evaluation signal, this evaluation here, to optimize the code snippet, powered by the well-documented ability of LLMs to simulate the human feedback, the ability of LLMs to self-evaluate, and the ability of LLMs to self-improve. Now, I personally think we are not there yet to have a perfect 100% accurate self-feedback, self-evaluation capability, and a self-improvement capability of our LLMs today. And this includes GPT-4 Omni, We have a lot of mistakes. Remember, the legal systems where 1/3 of all questions were completely hallucinated and not based on facts. As long as we have this performance of LLM, this self-feedback idea, this self-evaluate idea, and this self-improve idea, I handle with specific care. And I do not trust those systems. Let me give you, for my green grasshoppers, a very simple explanation what I just told you. Imagine we have here on the left-hand side an LLM. Let's call it an evaluator LLM or a teacher LLM. It is GPT-4. And this GPT-4, let's say, can handle a complexity level or causal reasoning level or logical deduction level of 6 out of 10. So really good. And then we have here our API channel. And then we have here, let's say, Mistral 7b. And Mistral 7b, complete level, reaches only 3 complexity level out of 10. And now, with this methodology, our task is clear. Eh? We want a prompt optimization for this LLM, Mistral 7b. So whatever the model is capable today, with this configuration, with this pre-training, with this fine-tuning that you have, you want to get the maximum out of this system. So you want to have the perfect prompt. So you run 100 tests or 500 optimizations with this natural gradient descent methodology that we have now in TextGrad. But careful, there is something like a complexity theorem. You have to be careful that you can establish a useful and beneficial communication between those two models. The moment GPT-4 outputs something for Mistral 7b that is too complicated in its semantic structure for Mistral 7b with a complexity level of 3 to implement, all this self-feedback and self-evaluate and self-improve fails completely. You have a hard interrupt here. The system is not able to understand what it could do because maybe its self-reasoning capabilities are not at all able to understand the input from GPT-4. There are some beautiful theorems here in the complexity theory that you can take this further if you do not have just a prompt optimization, but you have a system parameter optimization for designing new molecules in drug theory or in biomedical or whatever. So you have to be really careful with this configuration of LLM, that those systems, let's make it very easy, understand each other. And maybe I noticed if I dump down, make it less complex, the answer or the instruction here by GPT-4 for Mistral 7b, Mistral 7b finds much faster the optimal prompt. So you see, just a week, so I'm not really able to give you here any further details because I'm just exploring this myself, but I will do a video a little bit later on more concrete examples. I can show you here certain threshold in this idea. Beautiful. As I told you, we do not only are limited to prompt optimization and to find here a system prompt, because if you think that a system prompt is more or less just a parameter, or maybe a hyperparameter for a system, for an LLM, we can do another form of optimization, and the authors call it here an instance optimization. We directly treat a solution to a problem, a code snippet or whatever, or a molecule design, as an optimization variable. And this is the nice thing here. Like if we have a code instance that we would like to improve at the time. So this new framework produces here the gradients for and directly optimizes here the code variable. So you do not have to limit yourself to the prompt optimization, but you can go for any optimization variable of the system if you can describe it and if the system understands it. And if the system has a causal reasoning ability to understand if you change the molecular structure of a chemical compound, what would be the effect if the system, this LLM, has been pre-trained here on enough biochemical or structural chemical pre-trained datasets. So this now is, in my domain, science, much more interesting than DSPy, but it has its own limitations. Yeah, let's come to the result. Reasoning. Here the official table 2 from the documentation by Stanford University, solution optimization for zero-shot question answering with GPT-4 Omni. There's this famous Google proof question and answer data set, and with a chain of sort, GPT-4. So if we say, hey, restrict yourself to chain of sort, we have an accuracy of 50%. And you might say, what? 50%? That's it? Yes, this is it. If you look for the best model you can imagine, complex chain of sort, tree of sort, graph of sort, combined with self-reflective and whatever you like, we achieved today, June 2024, 53.6% accuracy. A little bit more than half. Now, if we use TextGrad, I personally would have expected a better performance, but it is 55.0. These are the data. Now, if you go here to different data sets that are specific for reasoning, and I showed you in my last video, so you have comparable performance data, you see here the jump from TextGrad to a chain of sort is from 85.7 to 88.4 or 91 to 95. This is nice, but not really as powerful as you would have expected. But on the other hand, if you go from 91 to 95, this is great. So maybe dampen my expectation a little bit and have a look at this. Yeah, reasoning, real easy. You are immediately familiar if you look here at the example by Stanford. The system prompt, you treat this now, as I told you, as a variable. So the system prompt is now here simply, hey, you are a helpful language model, think step by step. Wow. And then you say here the role description, system prompt to the language model. This is exactly what is your system prompt defined. And then you set up the model, and you have here the Blacksburg LLM, where the system prompt is our defined system prompt. And then, as you know it from PyTorch, it follows the same thing. And this is the nice thing now, where Stanford argues this is 80% here of PyTorch. If you understood everything behind it, yes. If you're new to the system, I looked at the publication and I said, I don't understand a thing. So you have an optimizer, beautiful. Now you have this function textual gradient descent that you now understand what is the theory behind this. And then you go like you have normally, you have your forward pass, you perform the backward pass, you compute the gradients, and you update the system prompt. It is logic, it is what we know, and now we understand the theory behind this, and you have a new library that you implement. Beautiful, open source, great. Let's come here to the final insights here. And let's stay with reasoning, because I am interested here in the reasoning abilities of LLM. And the author Stanford says, hey, as the paradigm of AI shifts from training individual large language model, vision language model, to optimizing now compound systems involving multiple interacting language models, vision language models, robotics models, all those components and all this tool use that we have in multi-agent system, we need now a new generation of automated optimizers of the system to find here, let's say, the best prompt when our multi-LLMs or multi-VLMs system communicate. So they are continue their research for better automated optimizer. But the optimizer here is already really nice. But of course, the next step is a network of LLMs. Now, TextGrad combines here the reasoning power of LLMs with the compositional efficiency of backpropagation to optimize the system. But you see here, the crucial word where it all hangs on is the reasoning ability of LLMs. And I find this so fascinating because, just a week ago, I showed you here 2 videos about how you can improve the reasoning performance of LLMs by grokking, and what it means and how you do grokking LLMs for an increased performance. So kind of the circle closes now, because if you want to increase the reasoning capabilities of LLMs, grokking seems to be the way to go. And no, it has nothing to do with Elon Musk or grokking incorporated for this ultra-fast inference time. This is a different effect that I showed you here in my 2 videos. Yes, beautiful. So here you have it. We have now, starting from DSPy, a self-improving machine learning system from Stanford. Now, after a year, maybe a little bit more than a year, we have now the next iteration, the next new technology that is based on DSPy and on Prodigy. But now this new TextGrad system can do so much more and goes deeper. Test it out for your domain knowledge, for your specific task. Maybe your performance may be different to my experience. So do not trust anything you hear on the internet. Go try it out yourself. You can use here the free Colab notebooks from Stanford University. But remember, you have, if you want to use GPT-4 Omni, you have to have an OpenAI key that you have maybe to pay, or if you're new, you have, I think, $5 free credits for you. So you can try this out, have a look at your particular task in your domain, and evaluate yourself is this new technology is as exciting as it was for me to test it out now. And I will go on and I will use TextGrad for my next videos, and I will show you and I will implement this also in my systems. And here we are. I hope it was informative. I hope you enjoyed it a little bit, and it would be great to see you in my next video.